somebody standing between you and the TV. Some fancy remote controls use Bluetooth or other signals, and it doesn't matter if somebody's standing in the way, the signal can still get there. Now, another interesting thing happened about in around 2003, 2004, there was a disease that broke out in Southeast Asia called SARS. And they didn't want this disease to spread all over the world. You know, people get on airplanes, and if they don't know they're sick, they might carry this disease all over the world. They set up infrared cameras in the airports. Anybody that looked like they had a fever was pulled off the plane and had to stay there. And they've been using them continuously ever since. They've been using them all over the world in international airports to prevent the spread of disease. The physics of light, it's all around us in our everyday lives. Our next topic is sound. And I want to convince you that sound is caused by something vibrating. If you have a speaker and you open it up and look at the inside, it has this cone-shaped object, and that cone vibrates in and out, and it pushes on the air molecules, and they push on their neighbors, and they push on their neighbors, and eventually air molecules push on your eardrum, and you perceive that as sound. Maybe you use a tuning fork to tune a musical instrument. They wiggle back and forth, and they push on the air molecules, they push on their neighbors, eventually they push on your eardrum. And even our vocal cords work the same way. In fact, maybe you can do this, touch your throat, and then sing a few notes with me. La-dee-da. Okay. Did you feel that tingling feeling in your fingers? That's the vibration from your vocal cords. That's the vibration from your vocal cords. So we have a little model that might help you visualize. This bucket is going to model my mouth, and that means it has to have a hole in one side. There we go. And this side will be like the vocal cords. I'm going to bang on it, and it's going to push on the air molecules. They're going to push on their neighbors. They're going to push on their neighbors. Eventually, they're going to push on that T-shirt, and that'll be like in somebody's eardrum on the other side of the stage. And that's how sound would move across the stage. So let's see if we can visualize that. All I have to do is hit the T-shirt. Boy, my aim is off today. But you get the idea. And that helps you picture how sound might move across the stage. Okay, the other thing we know about sound is that it's a wave. What does that mean? What do you think of when you think of a wave? Maybe something at the beach, a wave at the beach? Well, what happens when you go to the ocean? The water, it swells up, and it goes back down, and that disturbance moves across the surface of the water, right? The water actually doesn't move very far, but that disturbance moves across the surface of the water. And that's what happens in a wave. So I think the best way to demonstrate this is to have you do the wave. You remember this? It's been a few years, I know, but it used to be very popular at sporting events. So what we're going to do, we're going to teach you how to do the wave. We're going to start with the people sitting in the very last row up against the wall, okay? And we're going to do a countdown, or if you're the last person next to the wall, you'll be the one. We're going to do a countdown, and then you're all going to stand up and then sit back down at the same time. Now the person next to you is going to wait. Wait until the person on your right stands up, and then you stand up and sit back down, okay? If you don't feel like standing up, just throw your arms up in the air and put them back down, okay? You get it? So there's a little bit of a delay. Right? Now it's tricky here because you people have to look across the aisle at the people on the other side, but I think you can handle it, okay? Are we ready? Yes. Let's give it a try. I will warn you though, the audience this morning did it perfectly, okay? And you don't want me making fun of you the rest of the weekend, so let's do it right. Ready? 3, 2, 1. There we go. Good, good. Next row. Yeah, good. There. That's building some steam. Looking good. Looking good. Awesome, awesome. Nice. to the challenge. Good job. Now, did you get up and move across the theater? No, right? You just moved a little bit, right? Up and down. But that disturbance moved all the way across the theater. That's what happens in a wave. And we're going to demonstrate that a little bit more with this long spring. Oh, boy. All right, so I'm going to, we've got this long spring here, and I'm going to move this up a little bit and let go, and this little disturbance moves down the length of the spring. Let's do that again. I'm going to disturb this a little bit and let go. And that disturbance moves. Now what happens when it gets to the end? It bounces back, it gets reflected back. Now I'm going to put the little disturbances in by moving my hand a little bit. And I'm going to try to time it so that the disturbances I put in with my hand meet up in the middle with the ones that are bouncing back. Okay, that's called interference. They're adding up in the middle. How much is my hand moving up and down? Not very much, just little tiny disturbances I'm feeding in. But how much is it moving up and down in the middle? A lot, because all those little disturbances are adding together there. If this was a sound wave, it would be really loud in the middle. Now I'm going to go a little bit faster. Now in the center, it's not moving up or down at all. If this was a sound wave, it would be really quiet there. But those other two spots, it's moving up and down a lot. If this was a sound wave, it would be really loud there. Now, that's how noise-canceling headphones work. They listen to the sound around them, and they feed in a sound so that it cancels out right at your ear and makes it quiet. You can actually make it quieter by adding more noise to something if you do it just right. Don't try that at home. You have to do it just right. Should I go a little faster? All right, I'm going to quit while I'm ahead. And now we're going to try to do something really similar with sound and show you the sound does the same thing. So those are called standing waves. When we can get that pattern to hold like that, it's called a standing wave. And what we have here is a pipe with lots of little holes drilled in the top. And we have a propane tank. And so we're going to send some propane in. Come on. There we go. Okay, this needs to get turned down a little bit. Oops, wrong one. There's two knobs here. Okay, there we go. That's better. So we've got some flames, and of course flames are fun just by themselves, but we're going to do something really fun with them. I'm going to play a sound wave inside this tube. And when the sound waves get down to the end of the tube, they're going to bounce back, and at just the right frequency, just like with the spring, when I wiggled my hand at just the right frequency, we got standing waves. First with one big hump, and then two, and then more, right? So I'm going to try to do that here. We're going to start. So there are three humps. Now we're going to keep going. See if we can get 4. When you listen to that, you notice that I kept increasing the frequency. That's like me wiggling my hand faster and faster and faster. And we hear a higher pitched sound. And the next logical question is, well, what kind of sounds can we hear as human beings? So Kimmy's going to tell us about that.
Okay, so the standard textbook definition says that the average range of human hearing is between 20 and 20,000 hertz. That's a pretty big range, but today we are going to try to approximate the range for you, our audience. So I'll start by showing you about 250 hertz, and I'll work my way up to 10,000. And when we get to 10,000, we are going to conduct a little experiment. Now everyone can hear this tone, right? All right, so this is 250 hertz. Now, we're at 500. We're at 1,000, 2,000, 3,000, 4,000. That's 5,000 and 10,000. Okay, now I want everybody in the audience, even the adults and our stage crew, to please raise your hand if you can hear this tone. Now I want you to keep your hands up until you can't hear it anymore. And I'm going to increase the frequency. Okay, we are at 11,000, 12,000, 13,000, 14,000, 15. Okay, quick, everybody look around and notice that almost all the adults have their hands down. Yeah. Okay, why do we think this is? Any kids up front have an idea? Just shout them out. All right. I heard because they're old. I wouldn't take it that far, but it does have to do with age. You see, as we get older, we start to lose certain frequencies of hearing. So those higher frequencies are usually the first to go, which explains why you kids could still hear that tone while most of the parents in the audience couldn't, and myself included couldn't hear it. So this means it's extremely important for us to take care of our ears while we're still young, which means you should listen to your parents when they say keep the music down.
This is the physics show. I had to put one mathematical equation on the board. V stands for velocity, or the speed of a wave. That's equal to the frequency times this funny symbol stands for the wavelength. Now when we talk, we change the wavelength by changing the shape of our mouth. So if I want to make a low frequency sound, my lips kind of go out. If I want to make a high frequency, my lips kind of get pulled in. I'm changing the wavelength. The speed of sound doesn't change very much from day to day. It's pretty constant. So I move my mouth a certain way, and the speed of sound is fixed, and my voice has certain frequencies to it, and I sound the way I do because of that. Now, if we could magically change the speed of sound, if we could increase the speed of sound, and I continued to talk the exact same way, my voice would sound much higher pitched. Now we can do that by breathing in helium. Now I know what you're thinking. If there's a gas that's safe to breathe that makes your voice sound higher, is there one that'll make your voice sound lower? No, sorry. Yes, there is. We have it here today too, sulfur hexafluoride. So Kimmy is going to demonstrate this for you. But like most people, when you put them on a spot, you have to talk for this to be noticed, right? Like most people, when you put them on the spot and say, talk, they clam up. So I'm going to give her this classic of American literature, Green Eggs and Ham by Dr. Seuss, and she'll read from that.
That Sam I am, that Sam I am, I do not like that Sam I am. Do you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham. Would you like them here or there?
I would not like them here or there.